Apologies. Okay, so the meeting should be recorded. All right, go ahead.
Just a second. Okay, can we go?
Yeah.
So building on top of the last month presentation of soft actor critic. Well, the base paper was this one, and this presentation is gonna touch slightly two papers. First one, soft actor critic algorithm in application, where they namely added photo.
Rosalind, I'm gonna have
Yes,
to stop you. Your voice are a little low for whatever reason. Maybe
the
you
voice
could.
is low.
Yeah, now it's good. Now it's good.
Okay,
Sorry about
that's
that.
my position.
Probably, yeah.
Everything good now.
Yeah, everything else is good.
And the second paper, which adapts the soft actor critic to discrete action settings. So first, one more detail is that during the implementation, we noticed that we do not use the state value function here to update the, how do you call this, the Q value, the Q networks,
Mm-hmm.
as in the original paper. And instead what they do is just you use a more heuristic method. Albeit is quite similar. The result doesn't change much. So is everyone still fresh on the details, like the state value function computation?
I think I know what you're talking about, but maybe for other people, they might have to look it up the paper, especially if they haven't participated the first half of the meeting.
Okay, so I'll try to sum it up quickly. So
Mm-hmm.
here to update the Q networks, right? We do the mean square loss between the current state value and the target update. Q hat, which in this case uses the reward plus the expectancy over the next state of the state value function. But in this case, the target state value function, which is computed as equation 3. But in the implementation, they actually do not use this part anymore, and they instead replaced it with the second one. So here, instead of having the expectation over the next state of the state value function, they just use the same Q network to compute the state action value of the next state,
Mm-hmm.
following the current policy.
Mm-hmm.
And
Yeah, so they're
well,
basically replacing, instead of saying the value function of the current state, they're just using Q value of saying Q value of the current state and the Q value of the current state and the next possible actions. So like an approximation.
yes. And well, one might wonder, what does it change, really? And so here I got the benchmarks on the WenDB. Oh, awesome tool by the.
Ooh.
So you can see that in training. Which one is which? Okay, so the light green is the bit of the back state network. The other one is one with. It's not quite the result are.
Your voice is a little lossy again. Sorry.
Is it
Yeah,
okay now?
but I think there's a small echo as well. It might be from your secondary device.
Yes, actually, I'm also hearing myself.
Overall, good. Yeah, so it doesn't seem to be a lot of difference between the two approaches.
Yes, there is not much difference.
Mm-hmm.
So next point comes to the automatic entropy tuning. So as they said in the papers and also in the source code, here when they actually add the entropy bonus, the minus 0.580 in an ST, is actually a multiplication coefficient of which we call entropy coefficient. And depending on the path, it's hard to entropy coefficient will develop automatically things of vector critical and application. So the theory is actually quite heavy. This dynamic programming over time, and basically what they do is to constrain the entropy to a minimum target value, which they call target. But in this case,
Rosalind,
determined.
sorry to
Yes.
interrupt you again. Is there any chance? Yeah, is there any chance you could use your phone as an input device, Bunny?
That's what I.
Also, I think the device which is screencasting is not muted. That might be an issue.
Yeah, because it's like when we hear your voice, it's like 50% of the time it kind of gets lossy. It's like your voice suddenly become very low and then becomes normal again.
That's really weird.
Yeah.
Any improvement?
It's better now. Yeah.
But there's still the echo.
Right now there doesn't seem to be.
Okay. So can we continue now?
Yeah, absolutely.
Okay, so basically, we want to dynamically edit the entropy coefficient during the training, and they propose the following objective to obtain such entropy coefficient. So if you're interested in deduction, please read the paper. It sounds like black magic, honestly. So I will quickly go over this code to see how we do the automatic tuning, if you don't mind.
Mm-hmm. Yeah, of course.
Okay, the quality should not be good.
You're using your phone. You're using your phone as an input device, right?
Yes.
And what's your output device? What are you using to hear our talk?
Computer.
Right. So I think for the computer, you have to mute the. Actually, yeah. What about you use your phone as the output device, so you don't you hear the conversation through your phone as well, just mute the computer completely, turn off the sound and mute the computer.
Okay. I guess I should have done that. Okay. You guys still with me?
Yes. And you have
Okay.
you have two devices. Did you do the same for the other device as well?
I think all the devices don't even have a mic.
But if it had sound like that could interfere, I don't know.
I do not think so. Everything is off.
Okay, that's fine. Let's continue then.
Okay. So I don't know. I see. So first, the target entropy, according to the original author's implementation, they propose of this method, which consists in line of the time space. So I guess I can convert get the 3 minus 3 as the target entropy, and that's what makes to optimize this object. And as they said, it heuristic, so I thought we might actually have a discussion. around this element, the one factor.
Oh.
Here we just have to compute this. Also, for numerical stability, instead of directly optimizing for the alpha, as in the equation here, we instead use the log alpha. So here you have the tensor, which starts at 0, and the corresponding value, which I set 1.0, obviously, and the optimizer. And the next part, where the automatic entropy tuning comes in, is right after the new network and the policy have been updated. So here we resample the log probabilities of the actions of the policy, and well, basically we have loss function as I don't know. So factorize the alpha, it's the log alpha, and multiply it by log probability and the target dimension. And as a result, we should have the probability here. This report. At the beginning, if I remember correctly, the automatic entropy tuning actually gets a little more bigger, but the automatic method still converges to the same result. Somehow.
Let's see.
On the light, automatically tuned entropy version.
The other tip I think will be helpful for the comparison is if you sort of smooth the graph, they have like a parameters for you to do that, and it'll probably become clearly. Yeah, it feels very close.
So here again, maybe it's because the task is quite straightforward. There's not much difference.
Yeah.
But in general, it still works. Also, we can see that the entropy here is well, 0.2 is the default value when we do not automatically tune. And well, as you can see, it becomes quite low, but still we have a good performance.
Right.
Or at least a good end. So that's basically it for the automatic entropy tuning. And finally, for the discrete action settings, there was a few modifications to do over the original paper. Let me bring this up. So first one, we obviously have to change the policy and the Q values to reflect the discrete action case. So in the first case for the policy, thanks to Costa for awesome refactoring, by the way.
Oh, thanks.
After computing the logits of the observations, we extract the softmax and the log softmax, which will be used later during the computation. And there is actually a helper method, right, to get actions, which gives us the action probability and the log probabilities, but not the action itself. Yes, we do actually have the action itself. And after that, probabilities and log probabilities. So that's fine. And for the Q value, well, after having the logits, okay, for a given state, it gives us the action value of corresponding to each possible action. So far, so good. Not different of the Q network actually. And here, well, following the original paper, there is again this state value function, which is supposed to be used as a target for the Q network update. But in a similar way, we just use the Q network by sampling over the next state to do the updates. And in this case, one advantage of this method is that we can extract the full expectancy, because if you remember this case, does not respond. In the continuous case, we can only sample the action and compute the corresponding target. But in this case, the discrete action base case, since we have all the probabilities of the action, we can actually get a more accurate estimate of the state value function.
Yeah, so I have a question, if that's okay with you.
Sure.
Yeah, so I'm always a little confused about this part of the paper. So is it the case that for the continuous action space, you're doing a sample, therefore when you're calculating it, you're only doing it for a particular action? But since in the discrete action space we have all of the actions, that's why you basically do that for every actions. Is that a good way to understand it, or does that make sense?
Yes, I think that's basically it.
Okay.
Here, in the original case, well, we have to take the expectancy following the actions sampled by the policy. So in this case, I think it comes from the batch, right?
Right.
But here, once we just have the state, we can actually compute the full expectancy using all the possible actions. So it's more accurate in a sense.
I see. Okay.
Implementation note is that here it's formulated as a matrix multiplication, but obviously it's easier to do it in a vectorized way and then sum over the batch later. So once the state value function was updated, similarly, we also use the full action distribution to update the policy itself. And there is the corresponding version for the automatic entropy tuning too. So that's it. And next, let's see how it works in the source code. If you don't mind.
Yeah.
That should be pretty big actually. So define policy, define the values and the targets. At this part, it should be okay. So here during the updates, once we have enough samples in the buffer, what we do is sample the next action probabilities and the next log probabilities too. Okay, so since we do not use the state value, it kind of loses its meaning. But anyway. Okay, so here is the estimate. Okay, I see. So once we have the next action probabilities, we can compute the next VST plus 1, basically, which is a V next target here, which consists in multiplying the next action probabilities, in this case the PST plus 1, because it's the next action, and the Q value augmented with the entropy bonus, which is computed here. So like the Q ST plus 1 minus alpha next log probabilities. So I think everyone should be good so far.
Yeah.
And the Q backup, which incorporates the reward following. It's basically the same equation as in here, reward plus gamma and expectation over the next state. And do the mean square error loss over here and back propagate it. That's one for the state value update. I mean the Q network updates. And for the policy updates following this equation here, we sample again, not really again, but isn't this in the buffer?
So the S underscore OBS, that's in a buffer, right?
We have the state in the buffer.
Yeah.
But since Okay, I guess we need to resample because it's not necessarily. Okay, I see. So we need to resample the action probabilities and the corresponding log probabilities, and also the Q value for the current state. So here, well, it's only one network here, but in practice, we use the minimum between two Q values.
Yeah, for the notation, I remember. So if you see the notation in the PowerPoint, it's the expectation of ST from D, right? I think if you resample the action, then you will write the notation as ST tilde D. But if you don't resample the actions, it will be ST AT from D. Does that make sense? Yeah. So since
Yes,
we don't,
it's ST from D.
yeah, since we don't see an AT, that's why we need to get more resample the actions by using the get action method.
Yes, and it actually makes sense because for a given ST, we do not know if the policy that we use to get the action, which is in the buffer, is the same as the one we are trying to update here.
Right.
So, makes sense. And finally, once we compute this intermediate term, the alpha times log p minus the Q value, so here's the correspondence, and multiply it by the action distribution, and then sum over the batches and take the mean, which correspond to the expectancy, will give us the final policy loss, update the gradient. And for the automatic entropy tuning, as in the continuous case, it's basically the same, albeit it's quite less identity for that. And I think that's basically it. As a result, here are some benchmarks. I just tested on chord pole V0. Well, it converges quite quickly to 100 maximum. Chord pole V1 also same convergence. And however, on Lunar Lander, I am not really sure if that's the maximum we can get. Actually, I think I have a run where I have 1,000 points, but here it seems to converge to 300. I do not know.
Yeah,
but
there's
still we can see he's learning.
Yeah, of course. There's something we should talk about the Lunar Lander, but after this talk, after your talk.
Okay.
Yeah.
Okay. Well, actually, that's a good segue. I think I'm pretty much done here.
Okay.
Thanks for your attention.
Yeah, thanks. Thanks so much for presenting, and thanks for the great work on the on writing up the continuous the discrete action space and did the presentation.
No big deal.
Thank you. The presentation was great.
Yeah.
Thanks.
Anyone have any questions for Rosalind? All right. If not, Rosalind, would you mind turn off your presentation? Click the stop sharing, and and I'll present on my screen and sort of show some of the new developments. Also, there's something about the SAC discrete, maybe a bug that we need to address. So let me share my screen right now. All right, can you guys see my screen?
Yeah, I can.
Okay. So some of the improvements. So first of all, I did some refactoring of the SAC discrete and assay. A couple of things I did after Rosalind did his PR pull request on the self-directed critic. The first thing was I added some code to enable the script to sort of record videos. So it'll look like this, where you can see the agent's performance at different time steps. So, for example, if we're looking at PPO, we can click on it and see its performance at various time steps. It gives us a feeling of the agent's performance. Like in the beginning, step 1, the agent is performing really bad. Oh. Yeah, for some reason, the error and the download button is overlapped. But then as in later stages, the agent is doing a much better job at balancing the poll. So that's the first improvement we did. The other improvement not seen by here is we combine the replay buffer implementation. Oops. So specifically, before we were using a replay buffer from stable baselines, and now we're using a replay buffer from minimal RL. We actually did a benchmark on all of the methods, the put methods as well as the sample methods, and it turns out the replay buffer from the minimal RL is actually much faster. Both the put methods and sample methods are much faster. I'm guessing because they're using a DQ data structure. That way they don't have to worry about if the amount of experience exceeded the buffer limit, you're going to cut it off. That's sort of handled by the DQ data structure internally. So I think that might be the things that speed it up. But in any case, we use the same replay buffer for the SAC and the DQN now. So that's the second improvement we did. So I started doing this benchmark. So it's still running on our server. So sooner or later, you're going to be seeing a video for each of these environments. Right now, only Carpal and Lunar Lander was ran. So this is actually an issue because so if you see here, the SAC performs okay for the Carpal, but for the Lunar Lander, it's not performing well at all. I'm not exactly sure why, but this is something that I'll investigate. Maybe when I refactor the code, I messed up something. But I did notice something, which is so in the code, in the SAC discrete, when I ran the benchmark, I had this x equal to f.relu.fc3, but that's usually a bad practice because if you do that, there could be situations where the outputs of the last fully connected layer could be negative. And if that's the case, both of the outputs will be 0 and you will have no gradient to optimize over. So that's always an issue. I'm going to take off these and see if that helps with this issue. But I'll investigate into why this is not performing, especially since Roseland just demoed that in his code base before this refactoring, the agent was performing just fine. But yeah, that's also, they had this weird bug, I suppose. So for PPO, so the whole idea of this video recording is that it records the agent's experience at a perfect cube. So like episode 0, episode 3, 129, 28, 65, things like that. And then after you get to 1,000, you record the agent's performance every 1,000 episode. But for some reason, when we're using DQN or SAC, it's having these really weird number. But this is not our issue, so I think I'm going to follow up an issue in the weight and biases client GitHub repository, because this should not be happening. But yeah, that's basically what I have for the moment. Does anyone have any question for me?
You said the SAC might be performing badly after the refactor. Was there a previous run which was performing much better?
Yes, that's what Roseland showed me, right? Roseland showed us that for the Lunar Lander, it was performing just fine.
I think if you can access, I forgot to share the slide.
Yeah, if you could send a link on the either on the Slack channel or here, that'll be great.
Yes, I will send the 1TB link, the report link in this chat.
Okay. Yeah, and there's some really weird issues when I was doing the refactoring, and I was spending some time on it. Wait a minute, where is the... okay. Huh? Right. The other thing with the SAC, even with the card pull, is something that I noticed. Again, also might be an issue. It's very slow for whatever reason.
Yes, I have the same remark.
Huh.
I guess it's quite popular.
Yeah, let me see Rosalind's implementation real quick.
I think it's quite possible the last ReLU.
Yeah, do you still...
policy.
Yeah, you don't do the last layer ReLU, do you?
No.
Okay, so it's just the X. Yeah, so this is also kind of the reason why I don't want to do this, is because it's kind of hard to see exactly what's going on. So let me see. So for each layer in the last layer...
Except the last layer.
Oh, except the last layer. I see. You do the ReLU, and then... Okay. That makes sense. Yeah. All right, let's see if that finished loading up. Oh, looks like we broke it. Oh, never mind. It's good now. So you see this? Do you also? So one thing that's also a little different is Rosalind, when you did the evaluation, you had an evaluation function is essentially.
Yes.
But when I was running it, so you have this sort of evaluation return. Do you have a training episode return by any chance?
Yes, it's the train episode return. It's in the evaluation section.
Oh, over here?
Yes, that's the one.
Okay, I see. Right. So for the discrete case, you after I did the refactoring, you see there's like this void here.
Mm-hmm.
Yeah, I wonder if it's because of the last layer ReLU thing. Maybe that was an issue, but I'll definitely investigate into this because you don't seem to have that issue.
It's card pull V0, right?
Sorry, this is actually Lunar Lander, but even for card pull, I have the same issue. So let me see your card pull.
Okay, I send the link.
I already have access to it. I just need this to load.
No.
But yeah, I'm thinking that might have been it.
I don't know if the training was lucky, but there's no downtime.
Especially we're using the same seed. Yeah, this actually looks unreal. You know what I'm saying? Because how could you... Oh, I see.
It's too fast.
I see. It's here. Never mind. It's all good. Yeah, it's very fast. Okay, I can buy that. Yeah, so this is something that I'll need to come back and look after. But overall, I think this is good. And one thing I still need to work on is actually for the SAC file, I actually didn't include the entropy tuning, I believe. Yeah, there's no entropy tuning. So I'll add that to the SAC implementation, and then we'll basically be done with the SAC implementation. But even before we finish the implementation, I think it's good that if we sort of look into the project for the next development cycle. What do you guys have in mind?
Okay, before that,
Oh yeah. Do you have anything?
uh, did you do you have any insight on the target entropy heuristic?
That's kind of a weird thing. I have no idea actually, and it doesn't make much sense on top of my head.
So far in the original paper, I think you already saw how they define the heuristic, and there is an additional the Peter Christodoulou one where he just fixed it anyway.
Okay, interesting. And to be quite honest, I didn't quite read the entropy part, entropy tuning, because that was the I guess my focus was still on the first half of the initial paper, and the last two papers I was only focusing on the basically the Q value function stuff. So sorry about that. Couldn't really have a meaningful discussion about the entropy tuning with you.
One day.
Yeah, one day. But other than that, yeah. Do you have any additional comments or questions?
I'll ask it if it comes back.
Okay, sounds good. Yeah. So for the next week, I think it's we can for the were a couple of things we could do. We could sort of wrap things up with the. So I'll try to wrap things up with the SAC implementation, but at the same time we should start looking at new things. So I think Roseland was talking about maybe maybe looking at this paper. So the implementation matters in DBRL, a case study on the PPO and TRPO, and it looks very interesting. So for those of you who haven't read the paper, it's basically saying that the implementation. Excuse me. Let me find the specific part. Okay, I think this is about it. Right. So the paper is basically talking about in OpenAI's PPO implementation, they have these four things that are that are sort of not really talked about in their paper. The first thing is the value function clipping, and then the reward scaling and orthogonal initialization and layer scaling, as well as atom learning rate annealing. So they did a little experiments trying to see if they don't do these techniques, how would that affect the agent's performances in PPL. And what I found is that without these techniques, then the agent actually performs poorly, or at the very least not as good. So they found these sort of normalization techniques to be very important, and for a lot of people's implementation, they're not really using these techniques. So I think it's good that we look into this. But if we're not doing that, our initial plans was to looking at the DDPG paper. So that's two pathways that we have. I don't know if anyone else have any recommendations.
I think that
when it comes.
sorry, go ahead.
Sorry, go ahead. Go ahead.
A very long time ago, I worked on DDPT for like a robotic arm, part of some Udacity course. So I remember there was also clipping used in DDPT.
Oh, really? Okay.
Yeah. So there was one of the important things. I don't remember the other tricks we used, but they're mentioned in the paper. One of them was adding noise
Mm-hmm.
to the action values, I believe that was not the action values, some of the values.
Yes,
We added
because
noise using some process, on time object process something, and those seem to be critical. So the DDPG paper might also have some inputs which are useful for discrete spaces in particular, and might have something in common with the points that you showed us. The annealing for atoms is something that is very popular recently for deep learning. Like if you look at Jeremy Howard from Fast AI, this is something that he espouses a lot, and it seems that it has very effective returns.
Mm-hmm. Yeah. Okay. I think in that case, it probably makes. I think it makes more sense to do the PPO paper actually. Well, this particular paper, because it touches a lot of the tricks that not a lot of people are talking about. Um, so I think we should set a plan for reading over this paper, trying to do it for our next development cycle. Um, Yeah, let's set plans to do that. Oh, right. I was gonna mention. So there are also other techniques apparently, like reward clipping and observation normalization, observation clipping, hyperbolic 10 activations, global gradient clipping. So those are also the techniques that was originally listed over here as well. But I think they got reviews from the reviewers, and they decided to put that in the appendix. But I think it's also good to look at the techniques in the appendix as well. Yeah, that's great. Anyone have additional comments or questions?
just a remark
Just a what?
regarding DDPG.
So maybe for the DDPG, we can look at it the month after or something like that.
Okay.
Yeah, and also,
So,
go ahead.
so we do PPO.
Yeah, we do this paper. The implementation matters.
I see.
Yeah, what do you think? Do you still want to do DDPG instead?
No, I'm okay with either.
Okay.
My worry was that first do this paper, we should first do the standard PPO, and
Mm-hmm.
maybe TR to have a better grasp over each of the elements that have enumerated.
Oh, I see. I see. Have you read the PPO paper?
Yes,
Okay. Have you implemented PPO?
but my implementation really bad.
Okay. Yeah. So it could be a combination, right? If we're trying to implement this paper, it's necessary that we look at PPO and TRPO's paper essentially. So I would say we can even make this development cycle to be sort of a 2 months development cycle, because one thing that I found is implementation, takes a lot, takes a really long time to get everything right, and debugging with deep reinforcement learning algorithms is very difficult sometimes, and sometimes you're stuck for days, um, and a lot of us have obligations in jobs or schools, and we probably can't put into that much time into it every week. So maybe for this paper, starting with this paper, we can make a 2 months development cycle or something like that to sort of stretch the timeline to make it more manageable.
Okay.
But it's not a set thing, right? We can be very flexible and just see where things are going.
I just wanted to clarify. Are you talking about implementing this paper as an on PPO directly, or simply taking those points and transferring them to your current implementation?
Could you repeat your questions, please?
Yeah. So, do you want to re-implement the PPO with these, improvements, these tricks, or do you want to kind of take these tricks and port them over into your own implementation that you have right now?
So first of all, for those of you who haven't implemented PPO paper, one thing I would highly recommend is to take a look at the A2C file and try to keep a lot of the common structures. So, like for example, these parts, and then you can try to basically modify the algorithm-specific parts so that we have a common structure, and then we can discuss about this the modification you made based on the common structure. It makes helping each other easier. So if you're interested in implementing PPO paper, definitely take a look at the template of A2C and basically implementing PPO yourself. But for me, I already implemented PPO, and what I would probably try to do is read over the paper and just experiment with the 7 or 8 tricks that is mentioned in the paper and see how it affects the agent's performance. Does that answer your question, or?
No, I meant, are you seeing if it affects the PPO, or are you trying to put them into your soft types everything?
So for the TRPO, so that's probably going to have to be something that start from scratch. So I'll probably implement the TRPO paper as well.
I see. Okay.
Yeah, and it could be a joint effort, right? Everyone is encouraged to do their own implementations, and we can compare, and hopefully all of us learn more things about the implementations.
Yeah, definitely. So, I didn't give an introduction earlier. I just wanted to say that I'm just starting RL right now. So I'm a little bit behind the curve on you guys. And I'll probably catch up with you in a month or two, hopefully.
Yeah, absolutely. You're welcome to join the discussion and do what you can. And we're not experts. We're still learning as well. We're just students. But this hopefully will serve as a platform for us to discuss about a lot of implementation details and try to basically learn.
Good.
And if you have any questions, if you want to start out trying to get more comfortable with developing with RL, I guess especially using the common code base, this library, one thing I would recommend you to do is to implement reinforce. So that's one of the simplest reinforcement learning policy gradient methods. And you can just implement it. Again, also look at the common structure of A2C and try to keep a lot of commonalities as much as possible. And then just see if you can make the algorithm work with, let's say, a cart pull. And I have a reference implementation that I haven't posted in the repo. But if you implement a reinforced, we can compare and we can talk about the kind of things that if anything's different or to help you better understand things like that.
That sounds great. Thanks. Is about 2 1080 Ti enough for these kind of algorithms?
Beg your pardon?
I have 2 1080 Ti's on my local system. Is that like sufficient horsepower?
Are you talking about the GPU?
Yeah, the GPU.
Yeah, so the CleanRL supports GPU, so you can use it, no problem. So that's being handled by this line. So the device equal to torch.device CUDA if you have GPU. Otherwise, it's CPU.
Actually,
sorry.
In reinforcement learning, GPUs are not that important. I think most of the run Costa has run on CPU. If I'm not mistaken.
I think it depends. I think GPU speed up a lot when you do a lot of trainings. Like I think. Yeah, if you do, let's say the DQN related stuff, and if you use a GPU, I think it's a lot faster because you're doing optimization basically every step.
Or the pictures.
Yeah, or the pictures, yes.
So, to come back to Sajan's questions.
What kind of GPUs do you guys use?
Same as you, I think. 1080 Ti.
I have a 2060, but I don't think that's a huge issue. Even with CPU, it's mostly fine.
For example, SAC discrete, worst case, one policy, not just the policy, also the Q value, they just take about 400 megabytes of memory on the GPU. It's not really performance costly, so it's okay. As long as you don't do StarCraft 2.
Good.
Yeah.
What about running like multiple instances in parallel, aggregating experience from multiple agents at the same time, stuff like that?
So that's I can give you an answer to that. So that's something that is not really a huge priority for this library. The reason is that there are already a lot of libraries that does that. So, for example, stable baselines or Ray, RLlib, they all do this distributed training that can take multiple GPU or CPU devices. But it comes at it comes at a cost. The cost is that the code is significantly harder to read because of, if you want to do modular, if you want to do concurrent programming, if you want to do distributed training, you have to set up a lot of things such as worker and slave master, something like some sort of patterns. It makes the code a lot difficult to read. And if you look at a lot of the algorithms, the pseudocode is very simple. But then when you look inside of stable baselines, it's this very complicated structure. So the main focus of our library is to make it as easy to read as possible and easy to hack as possible. However, there is something that we can do about the making it faster. So one thing we could do. So this is something that I saw in the minimal RL. The way he does concurrent programming is actually really simple. So he does this. So he has an agent class, and he has multiple processes that shares a global model. So, yeah, just by the look of it, it doesn't look that complicated. But again, that's not a huge priority for this library. But if that's important to you, I have two suggestions. One is to, if performance is really important to you, maybe you can look at other libraries. The other thing is you can, implement this in ClingRL, this library as well, just to see how that would impact, if that will make the code significantly harder to understand or not really. So.
Got it. I just asking in terms of convenience in training. Like in my previous experience, it took like a day or more for the model to train. So I thought having multiple instances of stuff like that would make it faster. Sorry?
What was the task?
I was doing this Audacity's deep reinforcement learning course. So they were using the Unity ML environment, where they have a bunch of like standard environments to start with that use Unity, and Unity built their own sort of infrastructure. So they have this central thing called the brain, which interacts with the environment. It can fetch the state. You can give it the actions and stuff like that. So they have the infrastructure built in. They basically just took that as it is, and we worked with a few. For example, the DDPT was done on the Reacher environment, which has got a two-jointed arm, and you're trying to tell it to reach the target position. And in that paper, we launched like 16 or 20 instances in parallel, collected samples from all of them, pulled them together, and passed them into to our agent. Before that, we had one where this is a very simple ground. It's a flat ground plane scattered with blue and yellow bananas, and the agent has to collect all the yellow bananas but avoid the blue ones.
So it's basically a sampling problem.
I suppose so.
Because in reinforcement learning, for now at least, the sampling is what takes most of the time.
Mm-hmm. Yeah, I mean, a single run can take multiple seconds. It can depending on what your conditions are to end the episode, it could even take minutes. So if you have multiple instances of the environment running in parallel, it's much faster to collect samples.
I see.
But yeah, if you want to look into concurrent programming, sorry, go ahead.
We will burn the bridge when we get there.
Yeah. Okay. So I think this will be all for our meeting. Any last comments or questions? All right. Thanks everyone for. Go ahead.
Do you try Sack Discrete on Atari games?
Huh?
Yes.
Did you say something?
Yes. Do you want to try Sack Discrete on Atari game?
For Atari games, yeah, why not? Well, the thing is with the computational resources, well, we'll see what. If we want to try Atari games, I would say we should probably pick one that is the simplest because apparently for a lot of Atari games, they take a really long time to train.
Like 80 million samples.
Yeah, exactly. And we also need to adapt a different neural network architecture. So this is something that I want to look into as well. So most of them use convolutional neural networks. If you just use a linear layer, I don't think it's going to work. And you probably have to do some sort of grayscaling as well. And debugging becomes more difficult because it takes such a long time to train.
If you guys are interested in more like complicated structures, you can take a look at the Unity ML that I mentioned earlier.
Yeah.
Since it's built in Unity, you directly have access to all the parameters. So, all the in case of the robot arms, the angle of each joint and so on, the details of the environment are accessible directly. So it might be like this. You can take a look at the different standard environments that are available.
Yeah, that sounds great. All right. Thanks everyone for coming. Like always, I'll upload the meeting to YouTube and for future references. And thanks everyone for coming. And at some point before next Tuesday or Monday, I'll send out an email to everyone. Or make an announcement, just basically saying we're trying to implement the PPO case study paper. I guess this is what I'll reference it as to in the future, PPO case study paper, and we'll go from there. Thanks everyone for coming again, and hope you have a great weekend.
Thank you.
All right, thank you. Bye.